Hello everyone and welcome to the channel. In this video, we'll add input and output capabilities to the computer using a 65C22 versatile interface adapter. So I hope you enjoy. Alright, so in the past video, we've added this new RAM chip, so 512K of extended RAM, and we did some improvements to our ground distribution and our monitor circuit. Now, in this video, I want to add some input-output capabilities to the computer. And for that, I'm going to use the 65C22 Versatile Interface Adapter, also called the VIA. I'm not going to go into too much detail on this chip because Ben Eater has a bunch of videos where he uses this chip to do various things. And so it doesn't make sense for me to explain it again in great detail. But still, I still want to take a look at the datasheet and see if there's any interesting thing we can discuss. So let's get started. So first of all, what is the 65C22? If you look at the datasheets, it says that it's a flexible input-output device for use with the 65 series microprocessor family. The 22 in particular includes function for 2 peripheral ports. So there are 2 8-bit bidirectional input-output that the microprocessor can interface directly with. There are also 2 programmable timers and serial data transfer with serial shift registers. So this will add a lot of capability to our computer. If you look at the block diagram here, you can see there are a number of signals on the input-output side. And then on the CPU side, the CPU interface is a bit interesting because it is supposed to connect directly to the signals of the CPU. So you'll see there is the read-write, the reset, the clock, and then you have chip selects and register selects. So it's a bit different than the ROM and the RAM interface where you have a write enable and an output enable. The decoding for those are done internally to the chip. Now let's take a look at the pinout and specifically see if there's anything we need to mention with regards to hooking it up to the CPU. So the chip has 2 chip selects. One is active high, one is active low. And we're going to make use of both of them in order to connect to the chip. Then it needs the data bus. The IRQ output signal is active low. And depending on the version of the 6522 that you have, the IRQ pin is going to be a bit different. We'll be using the S version, which is the more modern one. The N version exists because of backwards compatibility with older versions of the chip that were used in legacy computers. But the more modern one is the S version. In the S version, the IRQ output is a normal output, whereas in the N version, it's only an open drain output. And so this means that if you need to connect multiple chips to the IRQ line of the CPU, you need to OR them instead of connecting them together. And it says here that this change was made to improve the low power, high speed characteristics of the part. Alternatively, you can also place a low voltage diode in series with the output to build a wire OR circuit. The datasheet then includes various schematics of the output buffers of port A and port B, and those are going to be also different. For example, the N version is going to have a current limiting resistor, whereas the S version is not going to have a current limiting resistor, but it's also going to have a bus holding device. So if the ports are floating, the bus holding device is going to weakly hold the value. And so you don't have to worry about floating inputs on this chip. And the same thing goes on for port B. The output of port B is going to be identical to port A on the S version, but on the N version, it's going to be designed quite differently. But we're not going to be using this one, so I'll skip it. And the datasheet also includes various other legacy versions of the 6522, so you can compare the design of the output pins. Continuing to take a look at the various pins of the chip, it needs the clock of the CPU, it needs the reset. There are 4 pins for register selects, and we'll be connecting those to the 4 lower bytes of the address, meaning we'll be able to address the 16 registers just by incrementing the memory address we are accessing. Then it needs the read-write and the power supply. So overall, it's going to be pretty easy to hook this up to our computer. There is just going to be one thing we have to pay attention to, and that's the use of bus enable and ready, as well as the valid address signals and how these are going to interact with the 6522. Because as you can see, it doesn't take those signals into account. and the decoding we did for the read and the write ports are not going to be used by the 6522 as well. So we have to keep that in mind. So this is our KiCad schematic. I'm going to add a new sheet to hold the GPIO. I need to make a bit of space here. And I'm going to copy the symbol for the 6522 from the 65XX library, which you can find on GitHub, which contains all the chips from Western Digital Center. And I will add it to the project. So this chips, of course, needs power and ground. And then we need to bring in signals from the CPU side. We need the data bus, the address bus, read, write, the clock, and reset to start. So let me import the pins from the top level. We also need the IRQ line and the first chip select for I/O. So let's import this at the top level. Okay, so these are the basics connected. So chip select 1 is active high. For now, we're going to connect it to VCC. The chip is going to be selected when IO0 is low. And in our address decoding circuit that we already built, this is the decoding that we do. And we have subdivided the IO space into 8 16-byte blocks. Since the 65C22 has 16 registers, we can just use the first space in its entirety to address the chip. So in order to see what's happening on the GPIO ports, I want to add LEDs to the outputs. And so for that, I'm going to duplicate what we already have in the debug module for the LED setup. So I will use the same buffer and the same LED bars to display the 8-bit data on the ports. So let me copy that. And I will create a bus named port A that contains all the signals of this port, including the control lines. So let me create that bus. And I will be using red LED bars for this data. And for red LED bars, we are using 1.5K resistor networks. Let's duplicate this for port B. And we also need to create the bus definition for this. Okay, so of course this needs a decoupling capacitor. Okay. And because we're now driving the IRQ line, we can remove this pull-up. All right, so I have here a 65C22. Let's start hooking it up. I want to apologize for the messiness of my wiring here. I know it's really bad. You probably can't see anything where anything goes on the videos, and that's not great. But The reason I'm leaving it as it is and not, cleaning it up more is that I want to move to PCBs soon. In fact, I was waiting for this I/O video to verify that I had all the necessary signals to drive the 65C22 before putting the glue logic on a PCB. So I think after this video, the next thing I'm going to do is do a PCB with the main CPU and glue logic board, kind of a 65C816 breakout board, if you will. And this will allow me to clean this part up, and it should probably help a lot. And then, of course, the end goal is to create a backplane system. But I'm still working on that, so I think I'm going to do intermediary PCBs, one for the breakout board, maybe one for the memory or the TNC, or probably maybe also the clock. We'll see how it goes. So this chip is going to add a bunch of mess on the breadboards because I'm going to need various control signals from everywhere on the boards. And so please bear with me for a couple more episodes while I get everything working and sorted before moving to PCBs. I'm going to add a new breadboard here for the I/O chips. And then the plan is going to use this area over here for the peripherals that are going to be connected to the GPIO. So the LCD screen, the keyboard are going to go here. Okay, so I'll leave some space for the 65C21 that I plan to add later. And I'll put this chip in the middle. Let's start hooking it up. So it needs power and ground. And a decoupling capacitor. I should probably turn off the power. So our IO0 line is going to come from pin 15 of the 138, which is this one here. That's going to pin 23 of the 65C22. And we need to pull up pin 24. That's the active high chip select. Then we need to bring in the data bus, which we have in the purple wires here. So let me cut all the wires for the data bus off camera. Okay, so these are all the wires cut. There you go. Now we also need the 4 first address lines. Need to remember to connect the power. And for now, I'll just use a jumper. I'll solder in a wire later. Okay. And then we need to bring the control lines of the CPU. So that's the reset, the clock, read-write, and RIQ. And I know it's not going to look great, but I will be using duple cables for this. So reset is on pin 34, and we can get it here from the main board. Then we have the clock, which is on pin 25. And the clock, we have it here. Then IRQ is on pin 21. And this we can get at the CPU on pin number 4. And now that the line is driven, we can remove the pull-up that we have here. And finally, we need read-write on pin 22. And this one we should have not too far away. That's this yellow wire here going to the TNC. And I'll have it go first to the 65C22. And then we'll go to the TNC. Now that the wiring is done, let me turn on the power to see that we haven't broken anything. And yeah, it looks like our memory test program is still executing fine. Now what we need is some LEDs here to be able to show the output. And I want to optimize just a little bit what I did here. On these 2 breadboards, you can see I'm using 2 breadboards for only LEDs and their buffers. And I feel like this should be only 1 breadboard. So I made a little prototype of what that could look like. I think I'm going to do a small PCB of this with the LED bar and its buffer, as well as the resistor array and a 10-pin header at the bottom. And so the idea is that I'll be able to plug it like this and display the data. Of course, this is only a prototype, but At the same time as I do the main board, I'll spin up some PCBs for moving those LEDs and gaining some space here. But anyway, I will be using this little module, to show the 65C22 working. So I need to connect the power and the ground. And then I just need an 8-bit jumper going to, let's say, port A. And port A's most significant bit is on pin 9. So this should be this way. So I just realized I forgot to show the underside of this, just in case you guys are interested how it's wired up. So there is this header here that goes straight into the buffer. I have the decoupling capacitor here, the LED bar, and then the resistor network. And as you can see on the bottom, power comes in here, goes to the decoupling capacitor and the input of the buffer. And then we have a ground line crossing over and going all the way up to the common pin of the resistor network. And then the data is just moving from component to component vertically here. So yeah. And also, I think this is nice because now I don't have to search for the right resistor whenever I want to use one of these LED bars. And if I want to invert them, I just have to switch from F541 to F540, and then it's wired the same. So I plan on having a few of these laying around in my parts bin. So now we should be able to test this. Let's go and write a simple program that will flash some LEDs using the 65C22. So I started by adding the memory map to our source file just as a reference, so we can know what's the addresses of the varying I/O chips and where's the RAM, the stack, the direct page. As you can see, I've added the VIA on the first I/O slot, and so the addresses of its registers are going to start at hexadecimal 7FC0. So here in the datasheet in section 2, function description, we can see the memory map of the internal registers. And so I'm going to copy this information in our source file. Okay, so here we go. Here are all the addresses of the registers of the 65C22. And now we can easily reference them in our code. So one thing I realized I forgot to do is initialize the stack pointer on resets. And so this is what this code is now doing. We initialize the stack pointer to 01FF. Okay, so now we should be ready to write some code to address the VIA. I'm going to keep it pretty simple for now. I'm going to use port A, and I'm going to set port A to output. Now we have to write FF to the data direction register of port A, because any bit that is set to 1 in the data direction register will make this pin go to output. And I will start by initializing it to 0. And then, so I'm going to keep the memory test program because I think that's useful, but somewhere in the loop where we are in 8-bit mode, I will just increment the port A register. And we should be able to see port A counting from 0 to 255. So let's assemble this and test it out. So it looks like I made a typo here, which means that all of these are wrong. This should be 7F8. Let's retry. Okay, so let's turn on the power. So it looks like port A is outputting FF, but it's never changing. When I'm writing to the VIA, the chip select is correctly selected. However, I have a wrong wiring with the address pins because currently they are all 0. And I think I shifted it by 2 places here. There we go. Now we should have the correct address, which is 3. And if I relaunch the clock, it's still not working. So let me just try to write something else than 0. Okay, so now it seems to be working. We're writing 555, and at some point we are incrementing by 1, but never again. So I think there's an issue with my program. So I've just added a bunch of increments here at the beginning of the program so we can verify that this works. Let's try it out. And I've just broken a pin on my EEPROM. Fun times. So here's another one where a pin was also broken, but I've soldered a header on it so I can still use it. So let's switch to this one. Okay, so let's run through our program. And then we set port A to output. So that's A9FF. And then we store A to the address of the data direction register. So we're doing now a write of FF. Then we load A with 55 and we write it at the address of port A. So this works. We have 55 here. And then we have the increment. So EE and the address of port A. So it should do a read of the address of port A, which is currently 55. That's good. And then it should write 56 to port A. This works. Then it reads it again. We get 56 and it writes 57. That works also. And so yeah, so this is correctly counting. So I'm not sure why it doesn't work in the rest of the program. So I'm thinking maybe that's because the accumulator is currently 16-bit here. We are only setting the indexes to 8 bits and presumably increment uses the accumulator. Let's test it by updating our instruction and let's see if that works. Okay, so the answer was staring me right in the face. I'm effectively changing bank for all data accesses. So of course, changing the data bank register is going to change the bank for when the CPU is reading the data here. So this is why it works on the first loop, because so far we haven't changed the data bank register yet. It's still 0. But then afterwards, each loop is going to have a different data bank register. And so this is not going to work. So what we have to do instead is reset the data bank register to 0 before doing the increment. And then afterwards, we can change its value. So let's do that now. So I'm going to use Y as well to store the value. I'm storing 0 into Y, and then I'm pushing Y to the stack. And with pull data bank register, now the data bank register is 0, so I can do the increment. However, I need to keep the value of Y from before this loop. So I'm going to push Y before overwriting it. And then if you think about it on the stack, we will have first 0, then Y. And so here we are pulling 0. And so we still have Y on the stack. So we need to pull it to restore its value. Otherwise, in the increment Y here, it's not going to work. And then we can push it again and use it to set the data bank register. So this should work. Let me remove my test code here, go back to 0 here, and then we can assemble this and try it out. Let's reset the CPU. And as you can see, we are now counting using port A of the 65C22. So that's great. Okay, so I've made another little 8-bit display because I want to show you something cool about the 65C22. And for now, I'm just going to put it here. There we go. Now, at the moment, we are incrementing port A in 8-bit mode. But if we look at the data sheet, we can see that port B and port A addresses only differ by 1 bit. And similarly, the DDR-B and DDR-A only differ by 1 bit. And so because the CPU is a 16-bit processor, if we access port B in 16-bit mode, it will actually write to port B and then to port A because the high bytes will get written at the address incremented by 1. And so if we use port B and DDR-B as well in 16-bit mode, we can use the 65C22 as a 16-bit output port. So let me show you a demo of that. I will set the accumulator back to 16-bit mode here. And I will switch to using port B. And in order for the demo to be a bit more interesting, I will do a right shift. And then here, I will move this to after we set the CPU to 16-bit mode. And then if I access port B, then I can use 16-bit quantities. So I have to set port B and port A data direction registers both to FF. And then I also have to write 0 to port A and port B. And just to make this more interesting, I will do 5555 just to have a more interesting pattern for the right shift. So let's assemble this. And I have a syntax error. It's not SRL, it's LSR. And I think I actually want the rotate instruction here in order to keep the pattern. Yep. Huh. That's weird. Oh well, I guess that works for the demo. So as you can see, we can treat the 65C22 as a 16-bit output using just one instruction in the assembler, just by targeting port B. And then 16-bit mode, the CPU will write to both port B and port A, leading to this result. So I think that's pretty cool. Okay, so now that we have hooked up the 65C22, we have to discuss what happens with the control lines of the CPU, specifically valid address, bus enable, and ready. So for valid address, it's pretty simple. We only want this device to be accessed when the address put out by the CPU is valid. And for that, we can use the active high chip select of the 65C22 to connect the VA signal. And now the chip is only going to be accessed when the address is valid. So we have to add that to our input-output. There we go. Now, what happens when bus enable is taken low? Well, the 65C22 as it is completely ignoring the signal. And if the address happens to be an address that points to this device, it is going to output to the data bus, at least in a read cycle. So what we want is for this device to be off the bus when the CPU is off the bus. This means that another device, such as a DMA device, could generate its own control signals and re-enable this chip. And so we don't have a lot of ways to do that. The only way is to use the chip selects. And it seems like what would be nice to do is if VA was actually tri-state and controlled by bus enable. This way, when the CPU goes off the bus, VA is tri-stated. And then this device is disabled unless something else is asserting VA. So for that, it's pretty easy because we have a few buffers that are still available here. So let me take this one. And it's going to be controlled by the inverse of bus enable. And it's going to give us VA. So we'll need these control lines. However, they're also needed here. And over here, we don't need to tri-state this line because it's already taking into account here. So we'll just remove this label and take it directly from the OR gate. And then the OR gate is going to go to the buffer. And this is going to give us the final VA signal. There we go. So now the 65C22 is only accessed when VA is high, and when bus enable is taken low, the 65C22 goes off the bus. Now the only signal remaining is ready, and what it does is it makes the bus behave as if the clock was held high. And so the way to transfer ready to the 65C22 would be to override the clock. However, we can't really do that because the 65C22 has timers, and those timers are relying on the clock signal to function. And if we were to stop the clock going to the 65C22, we would impact the measurement of time going through these timers. So we can't modify the clock going to the 65C22, and I don't see any other way for this chip to behave as if the clock was held high, and so I think we have to ignore ready for the 65C22. However, it's probably fine because the device is rated as 14 megahertz, just like the CPU, and so it will be as fast as the CPU to resume execution after ready is taken high, and so we probably don't have to do anything when ready is taken low. So let's go into the breadboard and implement these changes to VA. Okay, so we need to connect VA, which is pin 3 of the OR gate here, to the buffer on pin 12. So that's going to be the purple wire going to the output of the buffer on pin 11, as well as the green wire of the debug module. And then pin 3 over here needs to go to the buffer on pin 12. And then we need to connect VA to the chip select of the 65C22. Oh, and we need to connect, of course, bus enable to pin 13 in order to enable the buffer, as well as a pull-up on VA so that it has a defined state when bus enable is pulled low. There we go. And then we can take a look at the timings. So as you can see, the 6522S is specified up to 14 megahertz, just like the CPU at 5 volts. It has similar requirements on the clock as the CPU, meaning the clock rise time needs to be a maximum of 5 nanoseconds, and the total cycle time needs to be a maximum of 70 nanoseconds. So let me rebuild these in Rave DROM and we can talk about them. Okay, so let's take a look at the timing diagram of the VIA. So I have here the CPU clock at 4 megahertz. Now we know that the address and the read-write are going to be here from 10 to 30 nanoseconds after the falling edge of the clock. The VA signal is VDA and VPA, which take 10 to 30 nanoseconds, going through a 74HC32 and a 74AHC125. Each of those take 1 to 8.5 nanoseconds, which means that the VA signal is going to be ready from 12 to 47 nanoseconds. Then our chip select is going to be valid from 11 to 79 nanoseconds. And this is what we've computed in digital in one of the past videos. So the datasheet gives us the TACR and TCAR timings, and those are both a minimum of 10 nanoseconds. This means that the control signals must be valid 10 nanoseconds after the falling edge of the clock, which is the case because everything here is valid until 10 nanoseconds. And they must also be valid 10 nanoseconds before the rising edge of the clock, which is also the case here. It also gives us TPCR, which is the peripheral data setup. And if we want to read from a data port, the data must be on the port 10 nanoseconds before the rising edge of the clock. Then once the VIA has read that data, it will take 20 nanoseconds, that's TCDR, for that data to appear on the data bus on the CPU side. And it will hold the data until 10 nanoseconds after the falling edge of the clock, that's THR. And remember that the CPU read buffer, as we've designed it, requires data to be present on the data bus 19 nanoseconds before the falling edge of the clock and 9 nanoseconds after the falling edge of the clock. So in a read cycle, this is going to work perfectly because the data is output by the VIA a long time before the CPU needs it. So yeah, so this is the timing diagram of the VIA in a read cycle. Let's look at the write cycle now. So again, we have the same control lines and the same timings for when these control lines need to be valid, and that's TACW and TCAW. Both are 10 nanoseconds. So as you can see, this is working fine. Then we know that the CPU write buffer will present data 39.5 nanoseconds after the rising edge of the clock, and it will hold it until 10.5 nanoseconds after the falling edge of the clock. The datasheet for the VIA gives us these timings. It is reading data 10 nanoseconds before the falling edge of the clock, and the data has to be held until 10 nanoseconds after the falling edge of the clock. So that's TDCW and THW. As you can see, we are correctly writing to the VIA because the data is present on the bus at all times when the VIA is reading. And finally, once the write has happened, it takes around 30 nanoseconds after the falling edge of the clock for the data to appear on the peripheral ports. So that's TCPW. And so that was the timing diagram of the VIA in a write cycle. So as you can see, it will work perfectly with the circuit as we've designed it. Okay, so in this video, we've added input and output capabilities to the CPU. We've learned about the 65C22, and we've also discussed how to use the 65C22 in 16-bit mode. So this is pretty cool because it gives us input and output capabilities for the first time in this computer. So in the next video, I will be porting over some code from my 6502 build. Specifically, I want to connect the LCD and the keyboard interface to this new computer. And I'm not going to go into too many details on both of these because these are straight up taken from Beniter's 6502. So it doesn't make sense for me to repeat this video. So I will port over this code and then we'll be able to have a keyboard and a display interface. And if I have time in the next video, I also want to make some modifications to the Teensy. We need to solder this additional header here in order to get access to more GPIO ports. And this is going to allow us to have more control over the computer with the Teensy. Specifically, we'll be able to build a ROM programmer and build more of a debugger interface. So stay tuned for that next video. In the meantime, if you have any questions or feedback about this video, please let me know in the comments. And I hope to see you in the next one. Goodbye.